we went through the E1, and the E, let me make sure that it's a 1. The E means it's an elimination. Elimination reactions form double bonds. The 1, does anyone know, like, what does a 1 tell us? It's unimolecular reaction. So what that means, unimolecular reaction. What that means is that the rate limiting step depends on the concentration of only one species. So it depends on the concentration of only one thing. And so in the example that we had before, because I don't want to have to take the time to redraw the entire thing, so you can always look back at your notes. But that example that we had before, the rate is going to look, the rate law, if you write it, you always have rate, or V, for those who are in biochemistry, always use V. Rate is always equal to, what does every rate law have to have? The kinetic rate constant. It has to be a lowercase k. But then, then it's the concentration of the reactants, or the substrates, if you're doing enzymes, the reactants of the rate limiting step. Well, the rate limiting step there was, I'm just going to draw it as a carbocation. Okay. And that's because it's the rate limiting step for the formation of the carbocation. Remember, that was the slowest part. And so it looks something like this. This is not the exact example that we had before, but this is another one. So the rate limiting step here, which actually favors that direction, so I'll draw it this way. Rate limiting step or slow step was this. And so the only thing the concentration depended upon was this. Okay, technically it's the concentration of the alkyl oxonium ion dissociation. And so, but it's just, there's just one thing and one thing only that's reacting there. So that's why it's a 1. And so the E means elimination. The 1 just tells you that the rate limiting step depends on only one thing. Okay, so now, and that works best for tertiary alcohols, and we're going to find out for tertiary alkyl halides as well. But for tertiary alcohols, and the reason being, whoops, thought I had it on there, is this is the product. Tertiary alcohols work best. Why? What's so special about it? If you had started off with a tertiary alcohol in this right here, because this is the rate limiting step. So it's the slowest step. So what is it about the tertiary alcohol that makes it better than a primary alcohol?
It's easier to take off.
Why is it easier to take off? I mean, it is easier to take off.
There's less hyperconjugation reduction. I think there's less of the other molecules keeping it together.
There's less? Does anyone know? It's not that there's less.
The product has more stability.
Right. Well, this is the intermediate. This intermediate is going to be more stable than if it was a primary because of hyperconjugation and induction. There are more friends there to stabilize it. So remember, the tertiary carbocation is more stable than a primary carbocation. So since there's a carbocation formation, primaries won't do this at all. You'll never see it. Secondaries, it really depends. They kind of go a little bit both ways. And tertiaries, we'll find out, will only go this way. They won't go through the other one. If we have E1, we've got E2. Okay, so now I'm going to move on to E2 reaction. And so this is the E2 mechanism. This works best for primary alcohols. Okay. All right, so I'm just going to use like propanol, 1 propanol this time, as my example of a primary alcohol. We'll just write it out. It's still going to be acid catalyzed. So the reaction conditions are the same. And you still have to have at least one hydrogen on the vicinal carbon. It's also called the C alpha. And so and the reason why it's called beta elimination is because the hydrogen that's popping off, that gets pulled off to form the double bond is in the beta position because it goes alpha, beta, gamma, delta. And so it's 2 positions away from the ground zero, so to speak. Okay, so we still have an acid, because this is acid catalyzed. So an acid member is positively charged. And what's the rule of thumb when we see an acid? Protonate. And what can we protonate here? The OH. So the first step is identical between E1 and E2. It takes off the hydrogen, the electrons stay behind with the original oxygen. So that way you get a water. And you have this alkyl oxonium ion. So the first step is identical to what we had before. 1, 2, 3. Don't forget to put your charges. You don't want to lose points due to hasty errors. Okay? Now, don't write this part down. If this was E1, we'd have the water leaving, but, and like I said, don't write this down, this would become a C alpha, this would become a carbocation. It's a primary carbocation, and that will not happen because it's too unstable. Okay? So, and I forgot to put, this was fast, right? So, for the E2 mechanism, this is going to be the rate limiting step. So this is the slow step here. Okay? So I'm going to go ahead and draw in the arrow for it. Say it's slow. Since it's acid catalyzed, we have to get our acid back. So what do we have around in order to get our acid back? Think about what happened in the E1 mechanism. How did we get our acid back in the E1 mechanism?
Water.
By the water. And the same thing happens here. It's just 2 steps if it's E2. The 2 doesn't mean it's because it's 2 steps. The 2 means that the rate limiting step depends upon the concentration of 2 things. Okay, so here now we have the water. So first of all, this is the ground 0 carbon, so this is the C alpha. So I'm just going to put 1. Remember, there are actually 2 hydrogens there. But I'm just going to draw 1 in so that way it's easier to see what's happening. But we just have the water coming and swiping that proton. But these 2 electrons have to go somewhere, the ones that were holding the hydrogen on originally. So they're going to go to form the double bond. Boom. And then that water leaves. And technically, it happens simultaneously. It's not sequential. It's all as the water is coming in to take that hydrogen, the double bond is forming and the other water is leaving. Okay, so we end up with our product. In this instance, our product's actually the same. It's still propene. And then we get our acid back and we have a water molecule. So I'm just going to draw them this way rather than writing them all out. But those are the inorganic products. And technically the acid isn't a product because it's a catalyst. Okay, so this was E1. This was E2 mechanism. And that's because the rate here depends upon the concentration of the alkyl oxonium ion and the concentration of the acid. Okay. Because there are 2 things in that rate limiting step coming together. In E1, it was just a dissociation, so it was just 1 thing, but here we have 2 things that have to come together in order for it to happen. own, I want you to look at the E1 mechanism. I will type it out though. So on your own, look at the E1 mechanism of dehydrohalogenation. And the reason being is that there are a couple of caveats to keep in mind. Okay. One thing is it's weak base catalyzed. Okay, so instead of acid catalyzed, which the alcohols are, the alkyl halides are weak are base catalyzed. This one, usually we're talking about weak bases. So it's weak base catalyzed. And the second thing is if it's undergoing the one means it's the rate limiting step is only on one thing and it's analogous to what we've just seen with alcohol. So do you think it's going to work best with tertiary carb alkyl halides or do you think it's going to work best with primary alkyl halides for the E1? Say it with some conviction here.
Tertiary.
Thank you. That is correct. So I'm going to spell it out because they don't have a degree sign on this. Tertiary alkyl halides. Okay, and the reason why is because it has the same rate limiting step, the formation of a carbocation. The only difference is you don't form water. You're going to form, and you don't have a proton to protonate. What happens is the X leaves first, and then to form the carbocation, and then you go through, the base comes in and takes the hydrogen, and so on and so forth. But yes, the carbocation formation is the same. So look at that on your own, since it's not anything drastically different. The reason why I wanted to do this is because I wanted to spend more time on the E2 mechanism of dehydrohalogenation of alkyl halides. It can be seen with primary, secondary, and tertiary alkyl halides if you use a really strong base. Okay, so we're talking about bases that are stronger than hydroxide. So, what I was saying before, if it's E2, that means the concentration, the rate depends upon the concentration of two different things in the rate limiting step. But it's a little different than what happens with alcohols. Okay, so let me just type out some things here. So for E2, dehydrohalogenation, this is what they noticed. The observed rate depends on both the base, so what base you use, and which alkyl halide. The halogens are not created equal. And concentration of Rx. That's the concentration of the base and the concentration of Rx. That's one thing. Two, oh, whoops, not W, is that the rate depends on the identity of the halogen. So it depends on the identity of X. Okay. So I'm going to make a little table. Unfortunately, I won't be able to. I'll have to use my handwriting to do it. We have RF. And it's slower or worse than RCl, which is slower or worse than bromine, which is slower or worse than iodine. Iodine is the best at doing E2. And so we're going to compare just fluorine to iodine now, because those are the two extremes. Which has a stronger carbon to halogen bond? The fluorine or the iodine? Fluorine. Okay, so this one has the strongest of the group CX bond. This would be the weakest. Okay. Since in an E2 reaction, we're talking about which one is going to be the best at leaving, the best leaving group. It's iodine, because iodine when it leaves is when they both leave, they're going to leave as an X minus, and iodine is the happiest by itself. Remember, it's big and fat and everything, so it's the weak. Technically, scientifically speaking, they say it's the weakest weakest conjugate base. And so, if you're a weak base, that means you're really stable. Strong base means you're not. You're reactive. And so, since it's the weakest of the conjugate bases, it's the best leaving group. So this is the best. And then one is called leaving group Lg. This is the worst. Fluorine is the strongest of the conjugate bases. And so therefore, this is the slowest rate for these reasons, and this is the fastest. Now, this mechanism is awesome. I love this mechanism because it's just one step. So, guess which step is going to be the rate limiting step? Just the one. And so, that's why I didn't show the transition state and what the transition state looked like for any of the others. I will for this one, but it's the simplest of all of the reaction mechanisms. Whereas the E2, if you were starting off with an alcohol, you had to protonate first. Well, we don't protonate here, so there is no protonation step. So here we go. We have our carbon. Carbon has to have the X, which iodine would be the fastest if you were looking for speed and efficiency. The C alpha, the C that's next to the ground zero C, has to have by default at least one hydrogen. And then it's making two other bonds. You have to have your base. So I'm going to show it as a B minus. But a good example of a base would be like an alkoxide. So just think of ethanol and drop. An ethanol that doesn't have that hydrogen is called ethoxide. Well, ethanol is perfectly happy. Ethoxide is not. It wants to grab the hydrogen from someplace in order to become ethanol. So that's why those are called alkoxides. So hydroxide doesn't work as well here. It's kind of like the reference point of going anything stronger than hydroxide would be a strong base. Weaker than hydroxide would be a weak base. And so what do you suppose happens? Remember, we always go from things that are negatively charged or delta minus that attack things that are positively charged or delta plus. So what do we have that can do the attacking? The base. And it's not winning. And what will it attack? The hydrogen, because it's delta plus. Of course, it's just taking the proton. It's not taking the electrons along with it. So where will these electrons here go? It's going to form the double bond by smacking, bang, sound effects optional, smacking into that carbon. We can't leave that carbon alone because otherwise that carbon's going to have 2, 4, 6, 8, 10 electrons around it. So something must leave. The halogen leaves. So that is the one step. And it, by default, is the slow step. Because if you only have one step, it's the slow one. And I did state that I would draw the transition state for this. And I just drew that really, really big. So the transition state, this is not a separate step. That's why I wanted to point that out. But it's going to look like this. We have the B being delta minus now, coming and swiping the hydrogen as the hydrogen bond is breaking. The new bond is forming. The X is leaving. This is all happening at the same time, and this X is delta minus. Like I said, this is technically a transition state, it is not a step. To where our final products are going to be the alkene and the X minus, the weak base, whatever that was. So it'd be I minus if you start with iodine, Cl minus would be R minus if you started with either chlorine or bromine. Okay. And technically you have an HB, whatever that base was, it's protonated. All right. And so that's, the E2 mechanism for dehydrohalogenation, which is a little different than the E2 mechanism for the alcohol since you had to protonate first. Okay, so hopefully we've got that all done, and I want to show you, those were the simple ones. Now we're going to take it up a notch. Start looking at some real examples. All right, so we have the C alpha. And actually, I'm going to, for this time around, just to make it faster, I'm going to call methyls Me for those. It's the same thing. OH, H, CH3. Okay, and it requires an acid, my good friend, sulfuric acid. And we already mentioned the fact that it does have a C alpha, and the C alpha does have a hydrogen. So you would expect the following, okay? You expect to have a double bond between the carbon and the C alpha carbon, right? Because that's what happens. And so this would be what it would look like. We would have a carbon. The C alpha only would have 2 hydrogens on it. Of course, the alcohol is gone. So the ground zero carbon would still have this hydrogen and all of this. That's one of the reasons why I wanted to do MEs for methyls, because trying to redraw all that, it's a pain. And so it's going to have a C with 3 methyls hanging off of it. Okay, that's what you would expect. However, that didn't happen. Or I should say, in actuality, what is observed is that's your minor product. Only 3% of your product looks like that. And so, what happened is if you did this reaction, you're going to get 3 products. 3% of it is going to look like what you really expected. 64%, so I'll put a big but here. Literally a big but. Okay, so 64% of it actually looks like this. Methyl, 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 and a methyl. So that's the major product. 33%, I'll put it in different colors so it's easier to see, looks like the following. You're still going to have a double bond, obviously. But you have a methyl group, carbon, methyl, methyl, hydrogen. And like I said, it's 33%, so that's a minor product. And so the big question is how? How did that happen and why? How and why? So those two go hand in hand. And it's called a rearrangement, okay? So rearrangements can happen. There are two types. One's called a methyl or alkyl shift rearrangement, and one's called a hydride rearrangement. Okay? And what happens is in the beginning, faith integration there, in the beginning it's the same thing. You're going to protonate the alcohol. It's the only thing we got there to protonate. You're going to have it leave. You're going to get a carbocation. It's that carbocation that's the sticking point here. And so let's go ahead and draw. I'm going to redraw this so that way it's not as messy. Okay, so now we're doing rearrangements. And so in this color, once again, we have this carbon, the far end of carbon, which had the methyls hanging off of it. Carbon with the hydrogen, the alcohol of interest, and a methyl. We have our acid, which sulfuric acid under these conditions is going to look like an H3O plus or something. So we have our acid. And what's the first thing that's going to happen reaction-wise? What's step one? Anytime we have an acid, what's the rule of thumb? Protonate. Okay, and what can we protonate? The alcohol. And so two of the electrons from the oxygen and the alcohol swipes, boom, takes that hydrogen. The electrons that had been holding the hydrogen to the acid stay behind to make the water. Is this step going to be fast or slow? It's fast. Is it reversible or irreversible? It's reversible. Okay, now I'm just going to redraw. You draw everything that didn't change first. So we still have the carbon with the three methyls. Me. Sounds like my brother. In the love of Christ. There's another me. And our alkyl oxonium ion. It still does have two electrons around it. And then there's water, and I'm not drawing the, just for clarity's sake, I'm not going to draw the water products there at this point in time, because otherwise it's going to get really crowded. This now is going to be the slow step, right? Because that's just what normally would be happening. Since we have a secondary carbon alcohol, I should say, secondary alcohol, the water dissociates. So the water takes the electrons with it, and that's the slow step. So far, nothing new. Nothing's new. And so I'm going to redraw everything. The stuff that didn't change. We have the carbon and the me. And we lost it. Okay. CH, methyl, and this is a carbocation. Okay. And so this is where normally you would think, okay, the water comes in, takes the hydrogen, which I don't have shown right now, takes the hydrogen from this C alpha to form that double bond. But it only does that 3% of the time. So it means something has to happen. And I already told you it's a rearrangement. And this, they do a special arrow pushing for rearrangements, and it's really cool. I'll do it in this color right here. This one's a methyl shift. And so what happens is one of the methyls, it doesn't matter which one, I'm just going to do the one that's on the bottom because it's closest. It moves over, but when it moves over, it takes its electrons with it. And so it's just like, hey, I'm going to go to where the paths are greener, so to speak. And they do a little curly Q for the arrow. So instead of just doing a regular arrow, they curl it. And that shows you that the electrons are going along with it. And so whenever that happens, sometimes I'll even write out methyl shift. If it's a hydride shift, it's a hydrogen that jumps over and takes the electrons with it, because a hydride is an H minus. So this is a methyl shift. Now we draw the things that didn't didn't change. And this time I will draw everything out. So we have a carbon, still bound to the what had been the ground zero carbon. And this is the methyl that jumped over. Of course, this would be the far end methyl, and this is that hydrogen. This is the new carbocation, and it's going to have a methyl. And I'm going to draw one of the methyls out this way. Completely. You could draw all of the methyls out if you wanted to, but I'm just drawing it that way so that way it's not quite as busy. But all of those methyls are equivalent to each other. So now my question for you is, how many C alphas do we have to the carbocation? What kind of carbocation do we have now? Primary, secondary, tertiary?
No, primary.
Tertiary. And the reason why is because this is the carbon cation, and it's got 1, 2, 3 carbons attached to it. So it's more stable before. So expect the shifts whenever your alcohol, or alkyl halides can do this too, is next to a tertiary or a quaternary carbon. There'll be a methyl shift or an alkyl shift if it's a quaternary carbon. If you have a primary alkyl halide or alcohol next to a tertiary carbon, it can shift over as well to form a secondary carbon. Anything that's more stable. Remember, if you can do something that's more stable, then go that way. That becomes a major product or major intermediate. So we have 3, 1, 2, 3. All of them have hydrogens. I just drew this one out because it's going to be the same as that one. And so now we have our, let me just do a different color. We can have one, the last step, which is the fast step, is where a water comes and takes the hydrogen, the beta hydrogen. And so one way that we can happen is in this color, we have the water coming and taking this hydrogen, or one of those hydrogens, boom, that will form the double bond. And that's going to make that product that was 33%, okay? Because it's going to have, well, I'm not going to say why. But we also have another possibility. Because we have, and I'll put it in this color, a water here that can take this hydrogen. These 2 electrons can then go to form the double bond. Boom. And I'll let you go ahead and draw the products in. Okay. See if I can shift everything up to draw the 2 possible products. In this lighter color, draw your double bond. This C alpha, this C alpha, sorry. What will be hanging off of it in the lighter color? What are the 2 things hanging off of it? It took a hydrogen, so what are the 2 other things hanging off? 2 other hydrogens. And then hanging off of what had been the carbocation, what are the 2 things hanging off of it now in the lighter color? Right, a methyl. So I'll go ahead and write it out, CH3. And that's supposed to be a 3. And then we have the big thing, as well, I'll just call it. It's a C with a hydrogen and 2 methyl groups. Whereas in the darker color over here, go ahead and draw your double bond in. This is whenever it went to this side. what are the two things hanging off of, this was the C alpha. What are the two things hanging off the C alpha if it takes that hydrogen? Two methyl groups. Because I'm saying two CH3s. Almost sounds like I'm going to get tongue-tied. And hanging off of what had been the carbocation would be two methyl groups. So now my question is, I already told you which one was the major product. It's the one that was in the darkest color here. But why? Why is that the major product and the other one the minor product?
It's more stable.
It's more stable. The one's in the middle. What's the more stable is the Miss America one. World peace. It's more highly substituted, right? So that's the reason why I would expect you to say, and you should be able to name, thank you, you should be able to name that one, because it's going to be 2,3-dimethyl 2-butene. This other one, we have 1, 2, 3, 4. It's going to be a 1-butene. So it's going to be 2,3-dimethyl 1-butene. So, but just to reiterate, is you can expect a rearrangement. It's a rule of thumb, but just for, well, actually, I do have time to write it out. Because if I write it out, rule of thumb. Hey, that's one of my better looking thumbs. So you can, so if you see a quaternary carbon, or many times even a tertiary carbon, that is adjacent. I'm going to use the term alpha, but remember alpha means adjacent. That is alpha or adjacent to a functional group. That way, because it happens to both halogens and alcohols. Expect a skeletal rearrangement. That almost sounds like it's Halloween integration. Okay, if what's being rearranged is a tertiary carbon, it's usually the hydrogen that can leave, because the hydrogen is small enough to go along with it. If it's, or I would say it could be the hydrogen, if it's a quaternary, obviously it has to be a methyl group or an ethyl group or just any alkyl group, just shifts over because it makes a more stable tertiary carbocation. Okay, and so at this point, I'm going to go ahead and end class with prayer.